Hello, this is Dr. Hassan with Innovate, and this is lecture number 64, Equivalent Finite State Machines of Chapter 9, Design of Synchronous Sequential Networks of the course Digital Logic Design for Digital Systems or Digital Electronics. This is a disclaimer for you to read. I reference 3 books in digital logic design. However, there are many books related to digital logic design. In Chapter 9, we talked about the derivation of state graphs as the first important step in the design of synchronous sequential machines. Then we talked about practical applications, and then we started with the reduction of state tables, and we talked about 4 methods to reduce state tables. And today we will talk about a subject related to the reduction of state tables, which is equivalent state machines. Then we will talk about state assignments. Then we'll cover all possible implementations with flip-flops and programmable logic devices. Machine equivalence. Machine equivalence is defined as follows. Definition number 1, 2 finite state machines M1 and M2 are said to be equivalent if and only if for every state in M1 there is a corresponding equivalent state in M2 and vice versa. If there are 2 finite state machines, M1 and M2, such that each have a minimum number of states and M1 equivalent to M2, then both machines must have the same number of states. However, if machine M1 has more state than machine M2, which has a minimum number of states and M1 equivalent to M2, then we say the machine that machine M1 covers or contains machine M2. Hence, the covering concept between states and machines can be defined as follows. Definition number 2. State P of machine M1 is said to cover or contain state Q of machine M2 if and only if every input sequence applicable to state P is also applicable to state Q, and its application to both machine M1 and machine M2 when they are initially in state B and state Q respectively results in identical output sequences. Definition number 3, machine M1 is said to cover or contain machine M2 if and only if for every state Q in machine M2 there is a corresponding state P in machine M1 such that P covers state Q. Guidelines. Guidelines to determine equivalence between 2 finite state machines M1 and M2 are 1. Reduce the given state tables for the finite state machines M1 and M2 to their minimum number of states using any appropriate state table reduction techniques such as merger graph, implication table, or partitioning method, or even inspection method that we talked about. 2. If the reduced state tables from step 1 have different number of states, then machine M1 is not equivalent to machine M2. 3. If the reduced state tables from step 1 have the same number of states, apply the inspection method to both state tables using row matching or to both of their state graphs using graph matching to determine equivalence between machine M1 and machine M2. Alternatively, apply the implication table method with rows corresponding to states of one machine and colors corresponding the states of the other machine. All squares in the n times n implication table for n state machines must be considered. Example. Would like to consider really 2 states, 2 machines, machine M1 and machine M2. One is given in the state table A and one is given in the state table B. Now, we will apply the state table reduction technique to determine whether the 2 finite state machines are equivalent or not. Now, the state table reduction show me that those are the minimal number of states, okay, and we can actually prove this by inspection. I will leave this to you to do it as exercise. Now, also, if we inspect the 2 state table, we choose that S0 in M1 and state C in M2 because they have the same output. S0 has 0, 1 and C has 0, 1. So for the state A, for state C has to be equivalent to state S0 S1 has to be equivalent to A, and S2 has to be equivalent to B. So if we do that, you will find the two machines are really equivalent. S0 has implied pair S1, S2, and C has implied pair AB. Therefore, S0 is C if and only if S1 is A is equivalent to A and S2 is equivalent to B. Therefore, we substitute state S0, S1, and S2 in figure A with their presumed equivalent states C, A, and B respectively. We'll find the two-state table are identical. Very easy way to do it, okay, just by inspection. Now, as a second method, we can do it really by drawing the state graph for both machines. So visual inspection of state graphs may even be easier. The two corresponding state graphs of M1 and 2 are shown. We see that there is one exit line with the label XY, XZ is 1, 1, which is this one, and this one here between C and E. So if we rotate one machine by 90 degrees and match it on the other one, that you will see really a perfect match between the two machines visually. So in figure A, if we rotate the state graph in figure A counterclockwise by 90 degrees, then we verify all labels in both diagrams. So the graph matching easily can show you that S0 indeed will be equal to C, and S1 will be A, and S2 will be equivalent to B. Each state in machine M1 has an equivalent state in machine M2, therefore M1 will be equivalent to M2. But the method that I really like is the implication table. So inspection of state tables and state graph may be tedious and error-prone, especially when dealing with finite state machines having a large number of states. Therefore, we set the implication table with rows equivalent to one state, one machine, the states of one machine, and the rows equivalent to the states of other machine. So S0, S1, and S2, we have A, B, C. A cannot be equivalent to S0 because they have different output. See, A and S0, this one has 0, 1, and this one has 1, 0. However, really, if we look at A and S1, they can be equivalent if their implied pair C S0 are equivalent and B S2. And A is equivalent to S2 if C S1 and B S0. The same thing with B and S0, they cannot be equivalent, they have different output. B and S1, A S0 and C S2, and the implied pair for B and S2 is A S1 and C S0. These came really from the state tables. C with S1 cannot, so we put X and X in S2, and C with S0, their implied pair of their successors is A S1 and B S2. So in the second round, we check C S0, C S0, and E, C S0 is still there, so we leave it. A S2, A and S2, we need CS1. Well, CS1 is cancelled out, so we cancel out this. So this square AS2 will be cancelled out. The same thing with BS1, we have CS2 is cancelled out, so BS1, this square will be cancelled out, so put X on it. And so the remaining square is BS2, AS1, and CS0. So C is equivalent, S0 would be equivalent to C, S1 will be equivalent, to A, and S2 will be equivalent to B. S1 will be, none of those squares will be cancelled out, and this is the same conclusion that we arrived earlier. S1 equivalent to A, S0 equivalent to C, and S2 will be equivalent to B. And the implication table is the best way really to do it. Now the description of the table, I have it in writing for you as well as a reference. This will be the end of this lecture, which is the equivalent finite state, which is lecture 64. I thank you so much for listening. Please subscribe by clicking on the blue circle. Hopefully to see you soon in the next lecture. Sincerely, Dr. Hassan.